Bruno Puerto Real. This is Manticosa and Sean Di Pascal. We are the Meg Panthers, and we are doing the NASA Lunar Robotics project. The purpose of this project is to build and design a mining robot that can traverse the lunar soil. We have a weight limit of 80 kilograms. We also have a design limit of 1.5 by 0.75 by 0.75 meters. We have a 50 kilobyte transmission limit, and we're planning to implement a hybrid design, and where we have a fully autonomous control with with manual control option. The electrical team is going to handle the fully autonomous control, and they will be using the CME Camp 4 to do that. We also have a dust tolerant design and this requires all the components to be sealed. This is the terrain in which we will be doing the competition on, and the soil on which we will be on is called BP1. It has a density of 1.5 grams centimeters cubed, and fluff is 0.75 grams centimeters cubed. There will be craters scattered throughout, and there will be 1 foot by 1 foot, 1 foot wide by 1 foot deep, and there will be naturally occurring rocks.
Some of the design considerations we made when we were first designing the robot was what mobility system we wanted to use, whether it be wheels, treads, legs, or a hybrid of any of them. What motors we wanted to use to drive the drivetrain, and gearboxes, if any, were needed to either speed up or slow down the motors. For the collection mechanism, we looked at a few different methods, such as a scoop, conveyor belt, which would be continuously operating, and dumping mechanism, which would allow us to transport the collected regolith to a collection bin that's located on the side of the field. For the control system, we had several areas that we looked at, such as the sensors and cameras, which would allow us to visualize and navigate the field, and how they would adhere to the data transmission limitations that the competition set on us.
For the mobility system of the rover, some of the options we looked at, first were the wheels. They were the cheapest and easiest to implement, but it would give us a decent amount of traction. We then considered having a hybrid system to improve the traction, but it would also drive up the weight and the cost. So ultimately, we decided to go with a track system, which would give us the most traction, even though it would cost more and possibly allow some dust into the system.
For the collection system, we looked at two options, conveyor belt system or a scoop mechanism. For the conveyor belt system, we had an advantage of continuous pickup while incurring higher costs and higher complexity. For the scoop mechanism, it was simple to implement and had a higher, we required more power to run and had a limited excavation.
So the design changes that we made from our initial concepts to our final design, we shortened the overall frame length. We did that by placing the collection mechanism outside of the footprint of the frame. We switched to a thicker frame material while sacrificing weight. This allowed us to save time and money by making it easier to get that material. And we put a frame support on the collector in the front, which would be those two forks that you see, and on the dumping mechanism in the rear. The final design of the frame is constructed completely out of extruded 6061 T6 aluminum hollow tube, 2x1 for the frame and 1x1 for the collection mechanisms. The construction has it welded in all of the joints, the major joints, and pop riveted in all of the minor joints. We have roughly 6 inches of ground clearance between the treads, and the center of the robot is compartmentalized, which will allow us to organize the electronics as well as keep them dust-free. And the support of the frame that you see going up on an angle is also the integrated dumper guide rails that the dumper travels along.
The fabrication of the frame was done in 2 parts. First, the base of the frame. We ran a SolidWorks analysis using the Von-Mises stress criterion. We applied a load that would be more or less the maximum weight that the rover can be, and it gave us factor safety of 9. Afterwards, once we finished the design of the top section and completed it, we ran the simulation using an increased load, taking into account the regulator would have in it once it picks it up, and the factor of safety once the loads were applied where they would be experienced, it was 14.
For the drive system, we implemented a track system, and we use superjoy treads. They are sprocket driven. They have UHMV shoulders, and they also have a profile rubber tread. A side note, the UHMVW is a hard material which has an equivalency to Teflon in coefficient of friction. So as well, the sprockets that we needed from the company were too expensive, so we decided to manufacture our own by a CNC machine. We also, originally we had idlers in our design, and we decided to remove those because the belt itself started stretching, and we added tensioners.
For the gearbox, from our initial design to our final design, we went from a horizontal to a vertical orientation. Sprocket-driven output shaft, where the output shaft of the gearbox would be a sprocket that would be driven chained to the drive sprocket on the rover itself. That was switched to a direct drive, so now that the gearbox output shaft goes directly to the drive sprocket. And then, as you can see in the top right, we started with an open design, going to the middle, which would be a partially closed design, and then to the bottom, you see a cross-section view of our fully sealed design, which would prevent us from getting in. The final design of the gearbox, it's a 15-to-1 speed reducer. Operates in 2 stages. Each stage has a 16-tooth pinion going to either a 60 or 64-tooth gear. The frame of the gearbox itself is CNC machine 6063 aluminum tubing, 2x4. In that frame, we have press-fit bearings for all of the shafts. All of the shafts themselves are case-hardened steel. And for the dust covers, we had those 3D printed custom to fit over the case to ensure that nothing would get in and muck up the gearbox.
For the collector and dumping bin, some of the design changes that we had with those. For the dumping bin, we went from static to a mobile bin. It added complexities, but it allows us to lower the center of gravity of our rover while we're running. So this is done with a pulley system that would raise and lower the bin, as well as open and close the back door. And also with the collector, we are able to change it from a fixed to a variable depth collector.
This is our collector system. There's a video here. It has a continuous design. We use 2 AME 214 series gear motors. These motors were specifically used because when they're off, they don't backdrive. Additionally, the conveyor belt frame is moved up and down by 2 6-inch stroke actuators. And the belt, the chain on it is ANSI number 40 chain, a hollow pin chain. And each bucket is 12 by 3 by 2 inches, and there's 10 of them. The material of the buckets is ACM. This material is a composite of plastic and aluminum sandwiched together. It's a very hard material that we could easily shape by, and we populated the whole buckets together. Each bucket has a 0.75 kilogram capacity and is a 30-second dump cycle. This is our dumper, and 2 AME 210 series gear motors run it. We use UHMV pulleys, and also we use 1/16 aircraft cable that's sheathed. We use sheathed cable because it reduces the coefficient of friction. We also use elastic tubing to keep tension on the dumper itself, and we use ball bearing track lines.
For the depositing of the regolith, we used an AME 214 series gear motor, the same one that's on the collection mechanism. That is what raises and lowers the door. That is mounted at the top of the dumper on a cross brace, which is also made of ACM. The pulley that is on there has been 3D printed. The reason for that is the motor shaft is not perfectly round. It's actually got flats in it, so we 3D printed the pulley to have the flats in it already so it can be press fit directly onto the motor shaft without a coupler being necessary. We lined the interior of the dumper with PVC shower pan material. The purpose of that is to make sure that none of the regolith spills through cracks to the inside of our rover when we're in the collection phase, and also to help guide the regolith out when the trap door is open in the back into the collection bin. The dumper itself has a 25 kilogram regolith carrying capacity at roughly 75% fill, and it is a gravity-assisted deposit mechanism, so when the door opens, it is just simply the weight of the regolith, which is what's causing it to be deposited. This is our final design with everything working together. It shows how we would go about collecting. As you can see, we could drive forward and backward there. We would plunge into the ground for the collection of the regolith. However, since we're on a hard surface, we're going to raise it back up here so that nothing hits and breaks. The conveyor chain is going to operate now for about 5 seconds. That would be scooping up the regolith as we were driving forward and depositing it into the bin. The bin would then travel up the track, and then once it's in the deposit position, the trap door would open up and allow the regolith to escape into the collection bin. From there, we would reset simply by closing the door and then having the dumper go back down the track, being assisted by the nylon, elastic tubing, so that way it doesn't get stuck anywhere along the way.
For the control system, we had the manual control, which was spearheaded by the mechanical group, and autonomous control, which was taken care of by the electrical group. For the manual control, we use Telnet, which is a readily available program on any Windows computer. And we use an IP connection through a router to connect to the Arduino. The Arduino itself has an Ethernet shield on it. And we use an IP camera for visualization of the terrain directly connected to the Wi-Fi of the IP camera. We also use a keyboard, so we use WASD to control the movement of the rover. For the fully autonomous control, the electrical team implemented the CMU cam for tracking. It works by doing color tracking. And myself and Matthew, we did a previous test platform for the group, for the electrical group, and they tested out their design on there, or their camera on it and the program. The rover has IR detection for crater detection, and they're located in the front where the conveyor belt is located. Throughout the robot, there are IR sensors for avoidance collision, for collision avoidance. And we have relays for the dumper and the conveyor belt, and we have a micro switch for the dumper itself because so it doesn't break.
The electrical components that were used for the drivetrain itself, we were using motor controllers so we could variably adjust the speed and have more precise control. Initially, the electrical team spec'd out 2 RoboClaw 2x60 amp motor controllers. These operated 60 amps continuous draw with about 120 amp max draw. We ran into some problems there as the stall current of our motors were roughly 133 amps, so we actually burnt out one of the motor controllers during one of our testing phases. After getting it repaired and speaking to the company, they informed us that those motor controllers cannot handle our motors reliably. So we switched over to the Ford Victor 888 motor controllers. Those are also 60 amp continuous draw, but are capable of 150 amp burst. So they are robust enough for our motors. For all of the other motors in the collection mechanism, we're using 12-volt automotive relays. One of the issues we ran into with these was that the Arduino itself was not powerful enough to activate those relays. So what we did was we got smaller 5-volt relays that were powered from the Arduino, which were specifically used for activating the larger relays. For the power of the robot itself, we're using 2 8-amp-hour lithium polymer batteries operating at 16C continuous and 25C max burst draw. These provide us with more than enough time for our 10-minute match. We have a 150 amp main breaker to ensure that nothing on the robot gets too much current, as we blew up our motor controller last time. And then we are also, for another set of safety, we're using 40 amp auto resetting motor controller fuses on each of our motor controllers. For the sensors, we're using military specification wire. The purpose of this is that it has a high shielding rate, which will allow us to get the readings from the sensors without any pollution from the electromagnetic fields from the motors that they're here.
The global components of our project, as for the global awareness, before starting the project, we looked at some of the previous designs from other teams to get an idea of what direction we wanted to head in. At the competition, there's going to be teams from different countries, so we'll be able to interact and find out how they approach problems based on what resources they had. As for the global perspective, the lunar regolith contains helium-3, which can be used for energy production, and it can possibly set groundwork for lunar colonization. As far as the global engagement, throughout the project, as we progressed, we actually shared with some local schools of our project and how we were doing. And as we're actually going to communicate with them now to go back and show them how it's progressed now that we're almost complete. And our team is actually made up of 3 mechanical, 3 electrical, and 3 computer engineers. This is the timeline for our project. The orange, it starts in September and ends now in May, which is when the competition will be held. And what you see in orange is what we've already done, and the green is what we still need to do. This is the budget of each individual component. There's a lot. Our initial estimate was $5,000. Now the final cost was $6,200. The actual out-of-pocket was $5,200, and we got about $1,000 from donation and funding that we were able to get. These are some references. Any questions?
Very good. You're ahead of time.
We plan for the actual presentation to bring the rover in and we can.
Oh,
we
okay,
can
so you have
detail
time to put it
everything.
together and, okay, got it. You're using a lot of rivets for joining things and the regulation and all of that. Is that robust enough for a dynamic operation?
For the ACM is where we mostly use the rivets. That's the for the most load that it's going to be feeling is for the collection, where each one of the individual scoops is going to be going and collecting.
Yeah,
the
but that's a
rivets itself.
dynamic operation, so you
Correct,
got stress
yeah.
reversal, and I'm just wondering about the durability and sustainability of rivets on those kind of reversible
We
loading
used
conditions.
beefier rivets for those. We used, I mean, standard is 1/4 inch, and I believe we used 3/16 of an inch for the collection frame, and we made sure that, actually the first iteration, what you were saying, we were having an issue where the rivets didn't have a long enough grip length. And when we were doing our testing, one set of rivets kind of popped out.
That's my point.
And we actually found rivets with a longer grip length. They went completely through the material and mushroomed nicely at the end, and we actually used backing plates so it didn't pull through the material as easily.
Well,
And it seemed
just
to
in
solve the
case the
problem.
IAB folks ask you, be prepared to address that, because that just popped out and hit me. Due to the dynamic loading, we may not have the necessary durability to sustain those kinds of reversible loading. So we're trying to address that in some way, shape, or form.
Okay.
You mentioned that this is a multidisciplinary group. Is that multidisciplinary grouping right here, or is there some additional members?
There are additional members.
So are you going to have them here for the final presentation?
We will try to.
Their presentation is also at the same day at almost the same time, so
Oh.
we're going to try to have at least the team leader come for the
Okay.
electrical/computer side of things to at least represent that portion of them.
Okay, so that can be, you can work that out? I think it would be a good idea to bring someone who's very well informed in those other disciplines to come and support you, just in case the IB folks ask some questions in those areas. All right? I didn't see a lot of theoretical analysis, formula results that could be used to predict performance or stress behavior, those kinds of things that could also be compared with testing and evaluation. How do you respond to that?
We could definitely add that in. We have plenty
You
of
have it in the
calculations.
report?
Yeah,
For our gearboxes, we have all of the necessary calculations, and as well as the motors, how we have them spec'd out for the different mechanisms and how they're being controlled. and the
Yeah,
torque
you should
loadings on them.
bring some of that information in, even if you don't spend a lot of time on it, but you will demonstrate to the IAB folks.
Yeah, a lot of the stuff was done off of the calculation. We did the calculation and looked
Yeah,
for based on.
We'll demonstrate
Yeah.
that, because that's gonna be asked, okay? I can guarantee you on that. So let's see. Go to the slide on electrical components. Okay. Those components right there at the bottom, is there any way you can label them?
Sure.
Okay,
I see.
all right. And then go to your timeline slide. There's a lot of stuff I can't read there. So can you do something about that?
We could try to pull
Yeah,
it on there.
Yeah, maybe make the fonts a little heavier, bolder, sideways, top and bottom. okay?
Okay.
And are you aware of the rubric upon which you will be evaluated, the line items, because that's how you're gonna get your score, to make sure all of those line items are addressed in some way, shape, or form in your presentation. It may very well be addressed in your report, which they will also see, but some of the IAB members may not read the report before you get to the presentation. And there are line items there where you can get 5, where you can get 0, so you want to address that, all right? I didn't see any issue with units. You're reporting your units in what, USA or SI?
Yeah, generally, because the competition is based in SI units, but for our sanity, we switched over a lot of things to US units, but we kept the notations as SI with the US in parentheses.
Perfect, that's where I was going. Because you're gonna have the US audience here, so and some of them might not be able to do the translation in their minds to fully appreciate what you're talking about. I'm prepared for that, but I'm not sure all of them. So. All right, I have no other questions. Good job, thanks very much, and hope you will incorporate some of these comments to try and improve your presentation, and remember the dress code as well for next week. All right, thank you.